Bismillahirrahmanirrahim. Yes, hello everyone. This is Dr. Bassam Hamid. You're trying to solve problems of chapter 4 from the book of chemical process safety. And as you know, it's one of the best books by Daniel Kroll and Joseph Lover. And in this course, CHENG465, chemical process safety in industries, we have taken chapter 1, 2, and 3, and now we are up to chapter 4. So 4.1. So what we have at 4.1? It says 0.2 inch. Okay, so I have a 0.2 inch hole that develops in a pipeline containing toluene, so it's a liquid in a pipeline. The pressure in the pipeline, the point of the leak is 100 psi, pound per inch square gauge. Determine the leakage rate, QM. The specific gravity of toluene is 0.866, so I can get the density out of that. So what do I have? I have 4.1, and what you want to calculate is the leakage rate, which is equal to A into C naught into 2 rho GC into PG. And what is that? This is the equation of 4.7 that you can get, as you know, that this is like a flow of a liquid through a hole. Okay, we just said that there is a hole, so this is a flow of liquid through a hole. So this is what I have here. So I need to identify the values of A. So A most probably will be like pi d squared over 4. We will say that this, assume that this is sharp edged. So C naught will be like 0.61. Density, we can get the density from the specific gravity, like it is 0.866. So I just need to do some kind of unit conversion to convert it, which is usually multiplied by 62.4 to have how much pound mass per feet cube. And what else do I have? I have the PG, which is already given to me to be 100. So I'm going to just make this as that is because in inch, so I need to make this in pound per feet square. What else do I have? And I have, of course, the GC factor that we already know, which is 32.17. Okay, so all I think everything here that I already have. So I just need to start solving the problem, and for that I'm going to start with the area, pi d squared over 4, which is pi into 0.2 squared over 4, and you just make your conversion here, and you will get the answer to be 2.18 into 10 to the power minus 4 feet square. What about C naught? We said C naught is going to be 0.61 because we said that it is sharp edged. What about P? Okay, PG is equal to 100 pound per inch square, and I'm going to say I'm going to just convert that to be in pound per feet square. So I just want it to be in pound per feet square. Okay, what else do I have here? So I have the density, right? Density, which is 0.866. So I'm going to multiply this by 62.4. Pound mass, of course, per feet cube. Pound mass per feet cube, and this is going to be 54 pound mass per feet cube. Okay. So what I need to do now is to substitute. I have all my terms out there, and QM will be equal to 2.18 into 10 to the power minus 4. You check the units later. I'm just going to substitute. So that is 2 into 54 into 32.17 into 1.44 into 10 to the power 4, and by that you're going to get the answer to be 0.94, about 1. Let me write that just clearly. So that will be 0.94 pound mass per feet cube. Okay, sorry, pound mass per second, the mass flow rate, right? Great. So that was 4.1. It was straightforward. I know we're just trying to warm up here. We're just trying to warm up. Okay, so let's go to 4.2. So in 4.2 we say that we have 100 feet long horizontal pipeline. So it's 100 feet long. Let me draw that. So something like that, 100 feet long, right? This is my pipeline, 100 feet. Okay, and transporting benzene, so it's liquid, develops a leak 43 feet from the high pressure end. And when we took high pressure end, this will always be the high pressure. And when you have a drop in pressure, of course this will be the low pressure end, right? This will be the low pressure end. So talking about the high pressure end, a leak was 43 feet. So I'm talking about some kind of about like here, this distance of 43 feet, I'm having a leak here. Okay, I'm having a leak that's coming out from here. Okay, the diameter of the leak is estimated to be 0.1 inch, so I'm saying that the leak here is 0.1 inch. Okay, at the time the upstream pressure in the pipeline is 50 psig and the downstream is 40. So the higher is 50, the lower is the psig. So just to look at this again, so this is the upstream part where it is 50 psig. Okay, 50 psig, and that is the downstream part where it is 40 psig. Great. So what do we have here? So it says estimate the mass flow rate of benzene through the leak. So it needs to find Qm, and the specific gravity is given as 0.8794. So let me write that, so not to forget the specific gravity for benzene is 0.8794, and it's asking for Qm. Please tell me what is Qm. Okay, so that is the question. Now we want to find Qm, and if you remember the equation of Qm that we have for a hole, just for a hole, Qm is equal to A C naught into 2 rho GC into PG. Okay, so what do we have? Again, I can't find rho we have GC, we have C naught, A, which is the area of that hole, could be found. So what else do I have? It's PG. So PG is a new thing that I don't have, but actually we can find PG. Why? Because we just can't say that if the pressure drops from 50, okay, look at that. So if the pressure drops from 50 to 40, right? So if I consider that there's a drop uniformly, it is dropping from 50 to 40. At this point, what are the pressure is going to be? And from simple calculation, you're going to say just through simple math that, well, 43 over 100, like 43 over this 100, right? So I'm taking just like a ratio thing. If I multiply it, like into 50 minus 40, so this will be the place where it is, where we have this thing is happening. And of course I will add the beginning of it, so this will give me exactly what is the value of PG. Okay, so this is like simple math, and you're going to find out that that is equal to 45.7 psig. Of course I mentioned something here that I assumed uniform pressure drop, okay, and if uniform delta P, okay. So what do I have here? I have the value of PG, so all what I need to do is just substitute. Before I substitute, I just know I need to calculate what is A, which is pi d squared over 4, and in this case it is 3.14 into 0.1 squared towards 0.1 whole, right? And of course I'm going to do my kind of conversion, and this is going to be 5.45 into 10 to the power minus 5 feet squared. And of course C naught is equal to 0.61, so we are assuming this again because it's sharp edged. And for the row, okay, for the row again I'm going to multiply 0.8794 into 62.4 54 pound per feet cube, and the answer will be 54.9 pound mass per feet cube. Okay, and now we just substitute to find QM, and QM in this case is going to be 5.45 into 10 to the power minus 5 multiplied by 0.61, so that is AC naught into 2 multiplied by rho was 54.9 multiplied by GC, which is 32.17, multiplied by PG, which is 45.7. okay, in this case, after you do your whole part and taking into consideration, I think so I need to do some kind of conversion here. I'm not sure that I need to do some kind of conversion here, but it looks like 45.7 is PSIG. okay, so 45.7, because it's PSIG, I should have done that before, right? But I didn't do it. So what I'm going to do here, I'm going to say like I'm going to multiply it by 144. So this is one term. Okay, this is one term, just a unit conversion thing. So the answer is going to be 0.16 pound mass per second. So that's the amount that's going to be leaked per second. Now you just think that is per second, right? So if the amount was about that much per second, so within 6 minutes I'm going to having within 6 seconds I'm going to have about 1 pound mass, say half a kilo, right? If you're comfortable with the kilo, so that is in 6 seconds. If you just multiply that by 10 to calculate how much you're going to have in a minute, so within a minute you're going to have like 10 pounds, which is like 5 kilos. Imagine that is in a minute. Wow, then how much it will be in a half an hour just to wait for an emergency thing, or to close that hole. So just imagine how much we are going to lose. Okay, just how much we're going to lose. Okay, it's not about losing, it could be dangerous, right? It could be toxic, so we should be careful about that as well. So that was 4.2. Now let's go to 4.3, which says that the threshold limit value, the time weight average for hydrogen sulfide gas is 10 ppm. Hydrogen sulfide gas is stored in tank at 100 psig and 80 degrees Fahrenheit. So we have the pressure and temperature. Estimate the diameter of the hole in the tank leading to a local hydrogen sulfide concentration equal to the TLV. Okay, so we want to estimate the diameter of a hole in the tank, leading to what? Leading to a local hydrogen sulfide concentration equal to the threshold limit value. So we want to see this is the diameter that will lead that we get to this threshold limit value. To be careful that it doesn't get there. The local ventilation rate is 2000 feet per cube per minute and is deemed average. The ambient temperature is 1 atmospheric pressure. So here we have the threshold limit value, right? So if you just can remember that from the threshold limit value, in which we can represent as the CPPM, and I don't know if you remember the equation of the CPPM, which is equal to QM RGT over KQV into PM, and you just refer to equation 3.9. We have taken this. So what do we have here? So we have the CPPM, which we are going to substitute as a TLM value. So that is like the TLV value. We have the ventilation rate, of course, and of course we have the constant. We have temperature, we have pressure, we have molecular weight. And this is the K value in which we consider that if it is concentrated in one place or not. So we can assume a value of 0.1 to 0.5 if you can recall this, or is equal to 1 if it's really well mixed. And of course we're going to say that's from 0.1 to 0.5. And in doing that, I have all the values. The only thing that I have left is the QM. Okay, is the QM. And in this case, I'm going to calculate QM, and we are going to see how does that go from there. Okay, so let's work on it. So the information that I have here, again, I have here from 4.3, the TLV is 10 ppm. So I have CPPM, okay? So CPPM is equal to, so it's equal to 10 ppm. What else do I have? I have how to store in the tank 100 psig and 80 degrees Fahrenheit. So if I'm talking about 100 psig, and that is of course to the atmosphere, so the H2S is like it is stored at 100 psig, and here we are talking about a term. Here we are talking about a term that is what? That is in P, not in absolute, right? Value. So that will be like 100 plus 14.7. This will be 114.7. The PSIA. Okay, PSIA. What about the temperature? So this is like the pressure, and here the temperature is equal to 80 degrees Fahrenheit. To put it in Rankins, that will be 540 degrees. Rankine. So I think so we have all the values now. What else? I think I forgot the molecular weight. The molecular weight for H2S, that's 2 plus about 32, so it's 34 pound mass per pound mole. Okay, per pound mole. Okay, great. Actually, if now to identify the K value, to identify the K value, depending on what ventilation rate. But if you hear that in the question it said that the local ventilation rate is 2,000 feet cube per minute. So we have QV, and it's deemed average. Deemed average, that means if you go to the table, which is table 315, the K value given here is 1/8. Okay, so from table 315, we get the K value, as I said, that is average, and if the ventilation is average, K is equal to 1/8. Okay, so here it's equal to 1/8, and we have the QV is equal to 2,000 pound per feet cube. Okay, so I think so we have all the values. That looks really good, and all what we need to do now is to substitute, right? You need to substitute, and this will be the answers like that. 10 is equal to QM multiplied by 0.7302, that's the R, and that is multiplied by Rankine 540 into 10 to the power 6, divided by 1/8, which is the K value, multiplied by the QV. Okay, I don't want to put the units. Okay, and the last thing that I need to multiply by the molecular weight. Did I miss something? I think I missed the P. The P should be in atmospheric pressure. Okay, so before putting the M, the P is an atmospheric pressure, which is 1. Okay, it's about 1 into the molecular weight. So we are going to calculate QM in this case, and QM is going to be 2.16 into 10 to the power minus 4 pounds per minute, and if you want it per second, it's going to be 3.6 into 10 to the power minus 6 pound mass per second. You know what that means really? So you're simply saying that this is the amount to get to the TLV value, and imagine like how small is that amount. How small is that amount? Amazing. How small is that amount? Even with that small amount, we should be very careful. So it shouldn't be that much, so that it doesn't go to that threshold limit value. Okay, so that's the one of the calculations that we are really used to. Now, is it enough? Did we finish or not? Actually, we didn't finish. Why? Because if you go back to the question, it says estimate the diameter of the hole in the tank leading to a local hydrogen sulfide concentration equal to the TLV. So what I found here was just the leakage rate, right? The QM, but I didn't find the diameter. And actually, to find the diameter, in this case, we have like a gas within like a tank or something. So because I have like a flow of a vapor that is in a tank, that is like a leaking from a tank, and in this case, for H2S gas, okay, for the H2S gas, we can find actually what equation we're going to be using. I'm writing something because there's something in my head. Actually, before I should write this, for flow of vapor in a tank, we have QM chalked, and we always take the maximum QM just for safety reasons, which is equal to C naught A P naught into alpha GC into the molecular weight over universal constant into T naught, and that is multiplied by 2 over alpha plus 1, and that is to the power alpha plus 1 into alpha minus 1. And if you want to look at that, that is equation 440. So that is equation 440. And just to be more comfortable about that, let's look for equation 440. So that is flow of liquid through pipes. That's not the part that I'm looking for. I'm looking for gas through pipes. And I'm doing this search just like you're doing that search. And did I get through it? Flow of gases through holes. Okay, so that is flow of gases through holes, where we have the term for the mass flow rate, but then we said that this term for the mass flow rate is not the meant one, because for safety reasons we want to find that, as you can see here, for many safety study, the maximum flow rate. So we want the maximum flow rate, and that's why we took the derivative equal to 0, and we find QM chalked value. Okay, so that is the part. I forgot the divide sign here, so it's alpha plus 1 divided by alpha minus 1. Okay, so that is alpha plus 1 divided by alpha minus 1. Great. So this is what we have here actually. And now what? So that's not alpha, that's gamma. Now what is the value of gamma, right? What is the value of gamma? How we can get the value of gamma? We already said that if you go to table 4.3, you're going to find the value of gamma. Okay, and let me see where can I find the table 4.3? I think it's down or up. No, it's down there. Yep, that's here. So that's table 4.3, and if you go to H2S hydrogen sulfide, yes, what is gamma? Gamma, which is Cp over V, is 1.3. 1.3. Okay, so gamma here is equal to 1.3. So talking about alpha plus 1 over alpha minus 1, so we're talking about like this is like 1.3 plus 1, which is 2.3, divided by 1.3 minus 1, which is 0.3. Okay, great. So what do I have here? In this case, now what I need to do, I just need to substitute the term here. I have gamma. I have the molecular weight. Let me see. I have gamma. I have the molecular weight. I have the temperature. I have the universal constant gamma. I have the P naught. Okay. And what do I have? I have the C naught. C naught, because we said maximum, so C naught is equal to 1 in this case. And we already have the QM, the calculated QM that we have. In which case, in this case, we are going to consider the same QM that we had obtained. So we are going to find the area, and from the area we can get the diameter, which is from pi d squared over 4. Okay, so everything looks great here actually. So if I just want to find the area which is equal to QM chalked divided by the rest of the stuff. So QM chalked, which was obtained 3.6 into 10 to the power minus 6 of pound mass per second. Okay, So, and that is equal to 1 multiply, of course, if you want to know what's 1 is the C naught, and then multiply by the P naught. P naught was 114.7, and then this is multiplied by the square root of, going back, what was the gamma. If I want to calculate, this is the gamma here is 1.32. Okay, so the gamma is 1.32 into the GC, which is 32.17, into the molecular weight, which is 34. If you just want to take exactly, it's 34.1. I don't bother now like a lot about that. Over the universal constant, and the universal constant here is 1545. That fits all the units that are there, into 540 Rankine. And if you do this calculation, you're going to of course, that was, I forgot to multiply by 2 over gamma plus 1. So 2 over gamma plus 1, which is 2 over 2.3, 2 over 2.3 gamma plus 1, and to the power gamma plus 1 divided by gamma minus 1, right? So that was it. And if you do this, okay, if you do this, the answer will be 1.29 into 10 to the power minus 6 inch square. That is the area. And if I want to find now the diameter is just that simple, and that is equal to 4 into the area, which is 1.29 into 10 to the power minus 6 inch square divided by 3.14. The answer will be 1.28 into 10 to the power minus 3 inch square. And just imagine it's that, just that small, to have this little flow rate. Okay, this small opening of this little flow rate would cause that reaching to a threshold limit value. Amazing. Okay, so you can see like how things can be really sensitive, especially when we are dealing with some toxic substances, and we need to be very careful when we deal with the toxic substances. Okay, great. So that was the answer of 4 point. We just solved 4.3. That was the answer for 4.3. Okay. Now I'll be going to the question 4.7, and here what we are trying to calculate and get used to how to calculate the delta P, how much you are going to have a drop in pressure, and this is where we need the E over D, the roughness factor of the diameter, and knowing the Reynolds number, and then we calculate the fanning friction factor. You can recall this, right? Finding F to find KF to find F. Okay, so this is what I'm going to do now within 4.7. So 4.7, and this 4.7, what I want is actually to find delta P for flow of liquid in pipes. Okay, for flow of liquid in pipes. I do write this because I just want to make sure what I'm trying to target here, and let's read it just to make sure about what it needs. Water is pumped through a 1 inch schedule 40 pipe, interior diameter, so we have the interior diameter, at 400 gallons per hour. And by the way, even if it didn't tell us what is the interior diameter, we can get this from tables, but I mean, I don't want to get you to the headache of finding the table, so we're going to give you the information. Okay, because this is like a standard. Okay, so through a 1 inch schedule 40 pipe, which has the interior diameter of 1.049 inch at 400 gallons per hour. If the pressure at one point of the pipe is of 103 psig and a small leak develops 20 feet downstream, okay, 20 feet downstream that process, that pipe, compute the fluid pressure at that leak. So we want to calculate the pressure at the leak, right? And if we calculate the pressure at the leak, we found the P, right, the PG, and then we can calculate the QM, right? And if we calculate QM and we know the ventilation rate in that area, I can also calculate and know what is the CPPM, and knowing the CPPM, I can know that if it will exceed the threshold limit value or not. So you can see the trend of that, okay? You can see the trend of what we are trying to find here. So what is the fluid, the fluid pressure at the leak? The pipe section is horizontal without fittings or valves. So there are no fittings or valves, so we will not calculate any K friction factors for fitting or valves. It is horizontal, just to say delta Z is equal to 0. There's no work shaft here. So the water has, for water at these conditions, the viscosity, it gives us the viscosity and density to calculate Reynolds number, so that if you have Reynolds number and we have the roughness and the internal diameter, we can find the friction factor. So we can find F, K, F, and F. Okay, so it looks like it's like that. Finding from Reynolds number, and from the roughness, we can get the value of F. And getting F, we can find KF. And from getting KF, I can find my F, right? And this KF could be like many summation of KFs, right? It could be many summation of KF. So it's not only one kind of a KF. Okay, great. So to work on that, so what I need to do now is just to start doing my calculations. So from the mechanical energy balance equation, what do I have? I have the delta P over rho plus the delta U square over 2GC. I think I missed something here. I think no, that's correct. Plus that is multiplied by delta Z plus the fraction factor, and this is over the mass flow rate. Of course, there's no shaft work here, and this is horizontal, and this just becomes simple. And what about the delta U square? I mean, it's a good assumption to consider that as 0, where we are saying that there's no change in the velocity, okay? As if that we're saying that there's no change in the velocity, because we're talking about delta U square here. Okay, and if you look at the question, there's like, it's pumped, right? It's pumped. So we can say that it's like there's no change in the velocity. It will be a good assumption to consider that. Okay, so this will be even reduced more by saying that delta P over rho, of course delta P over rho, not dP over rho, because we are talking about incompressible, which is liquid. In this case, this is equal to 0. And here, so what do we have? We have delta P is equal to minus F multiplied by rho. And what is F? If you just can recall that F is equal to KF multiplied by U square over 2GC, right? And if you just know what is KF, KF is 4FL over D. So that is KF, right? So this is KF, and then the rest, which is U square over 2GC. Okay, so that is my equation here. So what I'm going to say, I'm going to substitute that here. So I'm going to substitute this here. So the delta P that I have is equal to minus 4F. Let me write that. Minus, it is 4 divided by 2, so it's 2. So it's minus 2. Let me write 2 here just to make it clearer. Minus 2FL U square rho over GC into D. Okay, great. So I think so things are becoming easy here. And if you go back to the equation, so what do we have? We have the diameter, we have the volumetric flow rate, and if you just divide what is the volumetric flow rate equal to? It's equal to area multiplied by velocity. Yes, so we can find the velocity from here. Great. And what else do we have? And we have the pressure also at one point. However, this is at 22 feet downstream. Okay, so we can make use of that. So we have one part of the P. We have, of course, the Reynolds number and so on, so that we can find the values that we want to find from the friction factors. Okay, great. So just to go back to the friction factor, so I need to find here, so I'm saying that this is good, this is good, this is good. We are going to find this, okay? This will need some kind of calculation, so this is good. Okay, so let's start doing it now and find the values, okay? And find the values. So we'll do it now one by one. The first thing I want to find is the U. Okay, so U is equal to the volumetric flow rate, and the volumetric flow rate, you remember, it was like 400 gallons. I forgot. Believe me, I forgot. So it was 400 gallons per hour. Okay, so that was 400 gallons per hour, and I'm going to just change this gallon into feet. It's always that the standard that you change things into feet, and so that is how much feet cube per hour I have, and I need to divide this. I need to divide this by the area, and the area is pi d square of 4. Okay, I did not find the area, so let me find the area first here. Where should I do this? Oh my God. Okay, so let me do it here. So area is equal to pi d square over 4, which is 3.14 into 8.8. The diameter, okay, the diameter, it is 1.049 inches, right? And if you want this to be in feet, so this is what you're going to do. You're going to divide by 12 inches. So that is pi d square. And this square, right? This is the diameter divided by 4. So you divide that by 4. You're going to find that the area is equal to 6 into 10 to the power minus 3 feet square. So after I find the area, I'm going to substitute my area here, 6 into 10 to the power minus 3 feet square. That is equal to 8.913 into 10 to the power 3 feet per hour. And if you put it in seconds per hour, if you put this in seconds, this will be 2.48 feet per second. Okay, so that is U, right? We found U now. Okay, well, what else do we need to find after we found U? After we found U here, I want to find F, right? And to find F, of course, I need the Reynolds number, and I need the E over D, which is the roughness factor of the over the diameter. So if you can recall, the Reynolds number is du rho over mu, or rho dv over mu, whatever you call it, is equal to 8.742 into 10 to the power minus 2 feet into 2.48 feet per second, 2.48 feet per second into 62.4, that is the rho, pound per feet cube, and that is divided by mu, and mu is 1 centipoise, and if you just make your conversion, this is 6 into 6.72 into 10 power minus 4 pound mass per feet centipoise, and that is equal to, the Reynolds number is going to be 2.01 into 10 power minus 4. Into 10 to the power 4. So it looks like it's turbulent, right? It's turbulent flow. So we can use the graph which shows that turbulent flow, or we can use an equation. Remember, I said that I will use the graph. It makes my life easier. Okay, so now what do I have? It said that I have a commercial pipe, right? I have a commercial pipe, and what do I mean by that? Let me see here. So what did it say? It says that assume new commercial steel pipe. So what do you mean by a commercial steel pipe? So if you go back and look for the commercial steel pipe, where's the commercial steel pipe? The commercial steel pipe. Did I skip it? Oh my God, I'm still searching. Okay, so the commercial steel, new commercial steel pipe, you can see here that E, the roughness, in millimeters is 0.046, in inches is 0.0018. Okay, so whatever you want, you just select one of them. Okay, so it's either say 0.0018 or 0.046 millimeters. So if I consider that, now I will select the difficult one, which is E is equal to 0.046 millimeter, and that was E. Why should I do this, right? I mean, it was much easier to just take the inch. Okay, I think it was easier to take the inch, right? So if you let me say 0.0018 inch, so that is 0.0018 inch, and we have the diameter is equal to 1.049 inch, and all what you need to do is you say E divided by D, and you're going to find out that this is equal to 2.00173. So you found E over D. So what do I have? I have now 2 into 10 to the power 4 and 0.00173. And knowing this, now I need to use this figure here. And if you just look by that, so it's going to 2 to 10 to the power 4. So here's 2 to 10 to the power 4. Let me see if this is helpful or not. So this is 2 into 10 to the power 4. You know which line I'm trying to target here. And if you go to 0.0017, okay, it's between these two. So it's like a line going between these two and then going up here between these two, and it just clicks here. Okay, it just clicks here, and that is about 0.007 something, right? So the F I have here is like 0.0075. Let me say in between. So here I'm going to find the value of F, which is 0.0075. So I found that from figure 4.7. Okay, I found that from figure 4.7, and I think so. I'm ready. I'm really ready because I have all the values that I need now. So if you just can recall the equation, it was delta P into minus 2FL and so on. So that was the equation that I have. Okay, great. So going back to the top here, so I will have the answer will be minus 2. So that is the delta P because it's dropping, right? That is minus 2 into FL U square into rho O divided by GC into D, and that is equal to 2 into the F, which is 0.0075 into L, which was 22 feet, right? It was 22 feet. If you just can recall, the question was saying that 20 feet downstream, right? So it's 22 feet downstream where you have that hole, into 2.48. We already calculated that value, which is the velocity, and that is U square into rho. The density is 62.4 pound mass per feet cube, and that is divided by, let me write this 62.4 just more beautiful. Okay, that is divided by GC into the D, which is the diameter, which was 8.74 into 10 to the power minus 2 feet. Okay, and getting the answer is 45 pound per feet square. Okay, pound per feet square. And if you want to present this like PSI, this will be equal to 0.313 PSI. If you can now, of course we are talking about here by minus, right? So it dropped out by minus 0.313. So that was a really little change in pressure, really little change in pressure. So a very little change in pressure that had been done. So it doesn't look like that affected that a lot. So talking about the delta P here, so so it's like that there was only a drop of pressure. There was only a very small drop in pressure, okay, which was 0.313 psi, and that's why I said in the beginning we are going to calculate how much we have drop in pressure. Okay, so that was for 7. finally, I want to solve for you for 8, which is enough for one session, I think so. So if a globe valve is added to the pipe section, compute the pressure assuming that the valve is wide open. So we're adding a globe valve, and the whole idea by adding a globe valve, so in 4.8, the whole idea by adding a globe valve, okay, when we add a globe valve, I just want to say that now we need to use the 2K method. In this case, what I need to calculate F, and my F now, I need to consider both the K pipe plus the K valve. Okay, it's not only that K only by itself. So my KF here, which is KF into U over 2GC. Now my K is not as simple as that, and I already calculated K pipe, which was 4FL over D, right? However, what about the K pipe, K valve? Now the K valve here is equal to the K1 over Reynolds number plus K infinity into 1 plus 1 over internal diameter. Okay, so that was the equation, if we can recall, that is equation 430. Okay, and what were the values? When you go to the values found what is for the globe valve, it's 1500 over Reynolds number, in which it was calculated, plus 4 into 1 plus over 1 over internal diameter, which is given to us. Okay, if you just go back, I just want to show that to you just to feel more comfortable. So I'm going up just to show you what I wanted to show you. Sometimes I forget. Yeah, the globe valve. That's not here. That's using the 2K method. Yep. So going and looking at the 2K method that we have here. So we have a globe valve. What is the globe valve? Yes, this is the globe valve. What is the value of K1? It's 1500 with the value of K infinity is 4. So that is 1500, and that's why it is 4 here. And by this, I already have the Reynolds number. I can calculate K valve, and that is calculate the K valve. Okay, and of course calculating K pipe. Let me see what's the value of K valve at the beginning. So that is going to be 7.89. And about the K pipe, we already said that this is like 4 into the fanning factor F into the 22 feet L over the diameter, which was 8.74 into 10 to the power minus 2 is equal to 7.55. And in this case, I have K pipe plus K valve, which is the summation of the K, right? The summation of the K, which is equal to 7.89. Okay, so it is equal to 7.89. Come on, how does that? How did we calculate this? It's going to be 7.89. Sorry for that. So that was 7.89. So I have the summation here 7.55 plus 7.89. That will be 15.4. And now to calculate delta P, which is minus 5 into rho, it is equal to minus K, of course, U squared for 2GC into rho. So we have the K value, and the rest we already calculated them before. So now just substituting minus 15.4 into 2.4, that's the U, into the density, which is 62.4 over 2GC, which is 2 into 32.17, and doing the whole calculation, you're going to find that is 0.64 psi. So the delta P is still small, even if we have a globe valve, which is in between, that's 0.1 and 0.2, and it's going to be minus 0.64 psi. Great. So that was a good job. We had done a great job solving many problems today, and looking forward to find you tomorrow at my YouTube video, where we are going to discuss, or we are going to solve more problems. All the best. Thank you very much, and see you soon. Massive.